This is the ECE 1215 Electroacoustics and Audio Electronics lecture on the basics of flat panel loudspeakers. This is what I did research on for quite a few years, and this is what I did my PhD on. And this is a pretty complicated topic, and there's a lot of ways to analyze this. I'm going to boil it down to just one little method of analysis. So we're going to talk about a lot of complicated equations, but then we're going to boil it down to one of the most important parts, which is being able to determine the resonant frequencies of the modes of panels. And so that's what I'm going to ask you to work on. So, a flat panel loudspeaker is basically made by attaching an exciter, which this is a picture of a little exciter. You can buy these on partsexpress.com. And these are basically just little loudspeakers without the loudspeaker cone attached to them. So they vibrate when you stick them to something, and what you stick them to is a board of some kind, a flat panel. So this is just a piece of poster board. You can stick it to metal or cardboard or wood or just about anything, and as long as you can excite that structure into vibration, you can get it to make sound. Here's a picture of a prototype that I made back when I was in graduate school. This is actually a piece of cover glass that would go over a flat panel TV. It's very, very thin glass. It's called Gorilla Glass. It's 0.7 millimeters thick, and there's an exciter attached to it. We place the exciter kind of off-center because that's a way to excite lots of different modes. We'll talk about that in a little bit, although I'm not going to go too in-depth into exciter placement. When you actually excite a panel into vibration, this is, at a specific frequency anyway, what the vibration would look like. And you can tell that the exciter would be placed somewhere around here because that's the highest amplitude of vibration. Of course, this is only at one frequency. If you were to change the frequency, these standing wave patterns would change. This is also a really blown up version, obviously. The surface doesn't actually vibrate that much. Usually it's on a scale of probably microns. But anything that vibrates is going to produce sound. So the vibrations mechanically are going to actually radiate sound into the air. It's pretty tough to mechanically configure these flat panel loudspeakers to give good sounding radiation. And so that's what I spent a lot of time researching and working on. One of the key aspects to doing this is just being able to pick the panel materials correctly in order to give something that doesn't sound terrible. And that's what I'm going to focus on right now. Some of the important parameters that are going to control the acoustic behavior of the flat panel loudspeakers are things like the panel material. So that's the density, the thickness of the panel, how homogeneous the panel material is. So for example, plastic is very homogeneous, but wood is not very homogeneous. So that does cause some significant differences. And internal damping. Internal damping you can think of in terms of like a wine glass. If you were to tap a wine glass, it'll ring for a really long time because it has really low damping. If you imagine a wine glass that's made out of wood and you tap that wooden wine glass, it wouldn't ring at all because the internal damping of wood is very high. So wood sounds very different from metal, which will sound different from glass, which will sound different from cardboard, etc. Because all of these material properties are different. So the panel dimensions are also important. That's just the length and the width of the panel. 1 centimeter by 1 centimeter panel obviously won't really sound like much of anything, but a 1 meter by 1 meter panel will produce a lot more sound. Large panels also are going to have much better low frequency behavior. The placement of the exciters is very important. I'm not going to spend a lot of time talking about this because it was essentially the topic of my entire PhD. So I'd have to go through quite a bit of complicated math to talk about this. But the placement of the exciters is very important. For example, an exciter placed at a panel edge won't excite the panel efficiently. If you place the exciter right in the middle of the panel, you're going to excite it very efficiently. And then the placement of the flat panel in an enclosure or a room. So if you mount the panel on some kind of a box, that's going to change the sound. If you mount it too close to a wall, that's going to change the sound, things like that. Enclosures actually do hurt the low frequency behavior of panels. They normally push those resonant frequencies up higher, and that hurts the bass reproduction ability. Alright, so let's begin by talking about a basic plate vibration equation. This is derived from the basics of physics, essentially. so I'm not going to derive this. It's a differential equation. It's d del to the fourth u plus rho h second derivative of u equals 0, where the parameter d is called bending stiffness. So that refers to how difficult it is to bend your panel. Del to the fourth is called the biharmonic operator. U is the space and time dependent excursion of the panel. So if I define U at a certain point in space, x and y, that's going to be a single point on the panel which moves up and down. So U can be a distributed function to represent the entire motion of the panel. So it would be in terms of x, y, and t. Rho is the density of the panel material, that's in kilograms per cubic meter, and h is the thickness of the panel. Let's dig a little more deeply into the bending stiffness parameter. That's d, which is equal to EH cubed divided by 12 times 1 minus nu squared. So the parameter E is called Young's modulus. That's intrinsic to the material and it's determined empirically. This has to do with the ratio of stress to strain, and it's a mechanical engineering parameter that you measure with special stress and strain gauges. H is the panel thickness. The variable nu is called Poisson's ratio, and it has to do with if you press on a material in a certain direction, how much does it expand in the other directions? So if you compress it by a certain amount in the x direction, does it expand in the y direction? And that's going to be measured empirically. For most solids, it's about 0.35, so unless a different number is given for Poisson's ratio, you can assume that it's 0.35. The biharmonic operator, that's del to the fourth, which traditionally is going to be equal to delta to the fourth over delta x to the fourth. That's the fourth derivative in the x direction, plus 2 times basically the second derivative in the x direction times the second derivative in the y direction, plus the fourth derivative in the y direction, which can also be written as the second derivative in the x direction plus the second derivative in the y direction squared. All right, so the solution then to that differential equation that I gave a couple slides back is normally given in terms of modes of the panel. So we're going to talk about modes that have an index r, and the modes are going to be written as the multiplication of 3 functions, a sub r times w sub s of x, y, and r times phi of j omega equals 0. So a sub r, that's just an amplitude determined by the exciter placement. So if you place the exciter in a place that doesn't excite the mode, then a sub r is going to be 0. If you couple very efficiently to the mode, a sub r is going to be 1. W sub s is the mode shape in space, which is the multiplication of 2 sine functions, one in the x direction and one in the y direction. These mode shapes, when you look at the absolute value, look like this for the first mode. That's when you have 1/2 period of a sine wave in the y direction and 1/2 period of a sine wave in the x direction. You can also have modes that look like this, where you have a full period in the x direction and half a period in the y direction. So this, for example, would be mode 1-1, because each direction has half a wavelength. This would be 2-1. And then this, for example, would be a full period in the x direction and a period and a half in the y direction. And this would be the 2-3 mode. So R in all of these cases is 1-1, 2-1, or 2-3. And then phi of j omega is equal to d psi sub r squared minus omega squared times rho h. This is what we're going to dig into more closely in order to determine the resonant frequencies, which are solutions to omega here. So if we think about a mass spring damper system, that's where you have a mass, a spring, and that is connected to some very heavy object. The mass has parameter m for kilograms. K is in newtons per meter. And the differential equation that describes this, as soon as you plug in e to the j omega, is k minus omega squared m equals 0. And when you solve for omega, you get that it's square root of k over m, which is the resonant frequency of the system. So when we go back and look at the equation here, we have the exact same form of equation. This would be k, and this would be m. And so then when we solve for omega, we get that omega is the square root of d psi sub r squared over rho h. And that's going to be our resonant frequency for the mode. So we know how to calculate all these parameters, and now we can figure out what the resonant frequency of a given mode of a panel is. Alright, so the only parameter so far that we haven't yet dug into is psi sub r squared. This is the solution to the del to the fourth operator as soon as you start plugging in the mode shapes. And what you get is pi squared r sub m squared over L sub x squared plus pi squared r sub n squared divided by L sub y squared. And that's all squared as well. R sub m and r sub n are the two indexes that live within R. So that's going to be r sub m and r sub n. So if we talk about the 1-1 mode, so R could be 1-1, that means R sub m is 1 and R sub n is 1. We refer to those as the mode index in the x direction and the mode index in the y direction, and together they just comprise the single index R. L sub x and L sub y are the length of the panel in the x direction and the length of the panel in the y direction. Alright, so let's do some example problems then using this equation. Example problem 1 is to calculate the 1-1 mode frequency for an acrylic panel that has the following attributes. The material parameters for acrylic are: the Young's modulus is 3.2 times 10 to the 9 pascals. That's 3.2 gigapascals. Rho, the density, is 1,180 kilograms per cubic meter. Nu, Poisson's ratio, is going to be 0.35. And the panel dimensions are that L sub x is half a meter and L sub y is 0.3 meters. The thickness of the panel is 3 millimeters. So the first thing that we want to do is calculate the bending stiffness D. D is EH cubed divided by 12 times 1 minus nu squared. E is 3.2 times 10 to the 9th. H cubed is 0.003 cubed. You have to put that in terms of meters, of course, so 3 millimeters is 0.003 meters, divided by 12 times 1 minus 0.35 squared, and that comes out to be 8.205 newtons times meters. Next, we need to calculate the modal stiffness, psi sub r squared. And that's going to be pi squared r sub m squared divided by Lx squared plus pi squared r sub n squared divided by L sub y squared, quantity squared. R sub m and R sub n are both 1 in this case because we're using the 1-1 mode. The 1-1 mode, again, looks like this. It just has half a wavelength in each direction, and it's the lowest frequency mode. So that comes out to be, when we plug in the two mode indexes and the length in the x direction and the length in the y direction, 22,243, and the units are 1 over meters to the 4th. What we want to do next is use those to calculate the resonant frequency. So omega is equal to the square root of d times psi sub r squared divided by rho h. So d, again, was 8.205. And newtons times meters comes out to be kilograms times meters squared divided by seconds squared times 22,243 times 1 over meters to the 4th. So these meters, that meters squared will cancel out. This will become meters squared on the denominator here. And then divided by 1180 kilograms per cubic meter times 0.003 meters for the thickness of the panel. This meter will cancel out 1 meter here and make this squared. Therefore, both of them have a meter squared in the denominator, so that cancels out. Both of them have kilograms in the numerator, so those cancel out. And we're just left with 1/2 squared as the units. Because there's a square root on the outside, the ultimate units are going to be 1/2, which are the units of frequency. So that comes out to be 227.06 radians per second. And when we divide that by 2 pi, we get 36.1 hertz. So what's nice about this is that the 1-1 mode of any panel is going to determine the low frequency limit of that loudspeaker. So if we put this low frequency limit down at 36.1 hertz, that's going to sound pretty good. That's a pretty low frequency. Example problem 2 is a design problem. You need to design an acrylic flat panel speaker that has dimensions L sub x is 0.3 meters and L sub y equals 0.2 meters. What thickness does it need to have in order to achieve a 1-1 mode frequency of 50 hertz? So we can use the same acrylic material parameters that we got in problem 1 to solve this. First of all, because omega is going to be equal to d times psi sub r squared divided by rho h, I'm first of all just going to look at d divided by rho h and calculate that. So that's going to be down here, which is equal to eh squared divided by 12 rho times 1 minus nu squared. So h is ultimately the parameter that I need to solve for. And Young's modulus was 3.2 times 10 to the 9th times h squared divided by 12 times rho, which is 1180, times 1 minus nu squared, which is 0.8775. And that comes out to equal 257,537 times h squared. Psi sub r squared doesn't have the parameter h in it, so we can just calculate that directly. And the only thing that's changed from the previous problem are L sub x and L sub y. So L sub x in this case was 0.3, L sub y was 0.2, and this comes out to be 127,023 1/meters to the 4th. So then to calculate the thickness, we do omega equals the square root of d divided by rho h times psi sub r squared. So d divided by rho sub h was 257,537 times h squared, and psi sub r squared was 127,023. So the square root of those have to equal 2 pi times 50 hertz. So ultimately, when we square all of this and get rid of the square root here, we get 98,696 on the right, and then a very big number times h squared on the left, and ultimately h comes out to be 1.74 millimeters. Alright, so you should be able to now use this to do all of the homework problems that I've assigned, which are going to be along the same lines as these 2 example problems. This is one of the key aspects to designing flat panel loudspeakers, is understanding how the materials are going to play into the acoustic radiation. So let me try and put some of this analysis into context for you. This is a graph of the mechanical response of a panel. And what you can see here are both simulated and measured responses. So I measured these using something called a scanning laser vibrometer, and I simulated all of this in MATLAB. So as we know, the solution to each mode that describes its behavior is a sub r times w sub s of x, y, and t times phi sub r of j omega. A sub r is the amplitude of each mode, so that's the height of the peak here in the frequency response. W sub s is the mode shape, so that's going to be these graphs, where we can see there's actually 2 1-1 modes, and that's caused by the exciter. So there's 2 peaks for the 1-1 mode. Here's the 2-1 mode, here's the 1-2 mode, and finally the 2-2 mode. There are many additional modes here. There's actually an infinite number of modes, but I only went up and graphed 5 of them. As you can see, the simulated graphs and the measured graphs are very close. The phi sub r of j omegas are the frequency responses of each mode. These are going to look like this. And what you've calculated and what you have to calculate in the homework are the resonant frequencies, which is the location of the peak of each mode. So obviously there's a lot more analysis that you can do than just calculating the resonant frequency. So the acoustic response of a panel looks like this. This is not the same panel that was simulated mechanically in the previous slide. but it's pretty close. It's just the resonant frequencies are in different places. So there are still two 1-1 modes which show up as peaks in the frequency response acoustically. There are additional modes at higher frequencies that show up as peaks as well. Anything in between a mode is going to show up as a dip. Now, unfortunately, what we want a loudspeaker to look like acoustically is totally flat. And as you can tell, a flat panel loudspeaker is pretty far from that. So a lot of the research that I did was using arrays of transducers or exciters on the panel to actually get a more flat response like this out of it. There's obviously a lot more analysis that you can do than just calculating the resonant frequencies, but that's one of the most important parts in the initial design stages of a flat panel loudspeaker.